right, okay, I see a few people went to go get a drink. I'm just going to entertain you guys for like 2 minutes so people can grab some water, come back. While I'm entertaining you, how many people have heard of the graph before? How many are familiar with the project, just so I understand where we're coming from? Okay. Okay, so people who are familiar with the project, how many of you guys are developers that have used it? Okay, cool, so a few. Okay, great. Oh, the images aren't loading. Okay, thank you. Great. Okay, hey everybody, my name is Camila Ramos. I am Developer Relations Engineer at Edge and Node, who is a core developer of the Graph Protocol. So the Graph Protocol has 5 different core developers now, and we all work on different parts of the project, and I work at Edge and Node. So that's kind of always a point of confusion for people. They're like, do you work at the Graph? Do you work at Edge and Node? Do you work at Streaming Fast? So today I'm going to be talking about a feature in a project specifically built by Streaming Fast, which is a different core developer that was built for the Graph Protocol. So just some context there. A little bit of background around me. I have 7 years. Before I became an engineer, I was in education. I taught kids how to code for like 6 or 7 years. I studied computer science. I went like a very traditional path for engineering where I went to school, and then I started off my career doing engineering at PayPal, where I worked on the checkout experience. So when you log out, when you pay, you can see the pay with PayPal button. That's the checkout experience. So I worked on that for a bit. So just to frame this talk, the title of this talk is Improving Indexing Performance by 100 Times. And this is all in the context of the Graph Protocol. We'll get into a little bit more about what that means. But just to set the context, I like putting this number up so people can really get an understanding and really just understand how much data is in a chain like Ethereum. So at the time of making these slides, which was like, I don't know, a week ago, this was the current block count for Ethereum. And in these blocks, you can fit about 70 or so basic transactions. And that's like wallet to wallet paying. This doesn't mean like deploying a contract. So it could be more, it could be less, but for the most part, it's this number around times this number of transactions that we have. And that's so much data. And you as a developer who's building dApps, who's building on the blockchain, if you're building your application, right, you're going to have a smart contract that stores some stuff on chain. So an example would be like if I'm building, and this is an example I use often, is if I'm building a dApp to find my biggest fans and people, I want to track who comes and watches me talk and who comes to my hackathons or something like that. I want to track it on chain. Who are the addresses that are showing up to my talks? So in my smart contract, I might have a function where when someone checks in with me or something, I execute some function that says, you know, this is their wallet address, this is the event, I don't know, this is the time, and then this is the count of events they've been to, something like that. And then over time, right, I might want to be able to say, give me all of my fans that have been to 10 talks or more, or who have been in 10 different cities with me or more, something like that. So this is all, you have this like wealth of data on the blockchain that you as a developer might be interested in at some point, especially if you're building applications. You're going to come to a point where you want to retrieve this data and display it to your users and kind of make complex queries that you can't really do manually the way it stands today. And yeah, due to the nature and the structure of a blockchain right now, there's no built-in mechanism to identify, categorize, and query for blockchain data. So if you guys have been on Etherscan or something like that, you know if you press the contract button, you can do a simple query like, I don't know, who's the holder of this specific token ID. You can get that back. Or what's the IPFS hash for this content URI. You can do very simple queries like that. But obviously, if you want to get into some of the queries that we just talked about, like, who have been to 10 cities and, I don't know, have been a member for more than a year, when you want to understand relationships between entities, when you want to do things like filtering and mapping, it's just not possible to do it manually, easily. So I'll get into it a little bit more, but there's a way to do it, right? You can do anything. We're programmers. You're going to figure it out. But the way that you would do it is you would either build your own indexer, which takes a lot of time and engineering resources, and just you as a dev or even as an engineering team, it's a really big lift. 2, for something like an NFT project or really anything, you could aggregate all of the metadata, aggregate all of these transactions manually, write some program on the client side to filter. You could do it, right? But it's not ideal. So that's where the graph kind of shines. So the graph is an indexing and query protocol that allows developers to efficiently read data from the blockchain. So the keyword here is efficiently. Like we said, there's ways to read data, there's ways to make queries, but the graph makes it really easy for developers to make these kinds of complex queries about data. So kind of a crash course here on subgraphs in the graph, because what we're going to talk about here is this is kind of the way that it's been done up until this point. And then I'm going to talk about substreams and this new feature that increases performance by 100x. So subgraphs are what we call these open APIs that you can build with the graph. And when I say open APIs, when we think of a traditional web API, it's a way for different web applications to communicate and send data back and forth, right? So this is kind of the mental model that we're using here of like, how can we grab this data from the blockchain and then send it to our dApp? So we call them subgraphs. And to build this API, a developer generates a subgraph, and you kind of just identify and work with 4 major components. So the first one is the data source. So you have to pass in a contract address or contract addresses. So in our case, in this example that we're talking about finding my superfans, I would paste in the contract address and say, this is my data source. Then we identify and we tell the subgraph what data we want to index. So for us, maybe for this example, it's like I want to index, every time this function that's, called check-in gets executed and an event is emitted. And in that event, maybe I'll expose like the wallet address, I don't know, the city, whatever I'm interested in tracking, right? Those are the things. And then in your schema, you create this model. So you say, my schema is going to be composed of a superfan, we'll call them. And the properties that a superfan will have is the wallet address, maybe the city that they're from, and then a current count of how many of my talks they've been to. So that's what I mean when we say we define the data that we want to index. And then next we define the events that we want to listen for. So, so for maybe people who aren't smart contract developers or just aren't familiar, there's this concept of events where there's kind of standard events in things like an ERC 721 contract, which is, maybe what you'd be familiar with for an NFT contract, where there's an event called transfer that gets emitted or kind of called when a token gets minted. So when it first becomes publicly available for sale, and then every time it gets bought. So it's a way to log these changes. So you, in your subgraph, you say, okay, these are the events that I want to listen for, and these events are the mechanism to make sure that you always have the freshest data. Because if, for example, I'm tracking my superfans, 5 minutes ago, maybe there are 20 people in here, and then if 5 minutes later 10 more people come in here, what is the mechanism to make sure that I get that refresh? How do I get these 5 new people? It's through these events. So when this function executes, this event is emitted, and then it triggers resolvers, which we're going to talk about next. So resolvers are just functions that are going to execute when these events are emitted to say, okay, something happened, something changed in our state. We're going to go ahead and run this code again to update what we want to know. So, in our case, how many superfans or something like that. So that's a crash course on how to build subgraphs. And then this little visual is, I like to show it, it's helpful just for people to see. So subgraphs live just below your client application, and you use them to display data. So they're kind of the layer between your smart contract or your L1 and then your UI. And kind of the problem that we're inching closer to with each slide here is that blockchains are optimized and have been optimized, and a lot of the work and focus have been around optimizing for writes. We talk about throughput and we talk about how many transactions and block space, but really a new problem or a problem that we're seeing emerging is that a lot of this stuff isn't optimized for reads. And as you said, as the years go on and as hopefully we do this forever, blockchains are on forever, they're just going to have more and more and more data available to us that right now there's not a really great way to effectively and really easily read this data. So speaking of reading data, just also a crash course on the ETL pipeline that's going to be important for the next thing we're going to talk about. Super simple. We're going to keep it really simple. So the ETL pipeline is this process that's an umbrella thing. So it's not just in blockchain, it's in traditional software. So we're taking this concept that's been around, and it's a set of processes to move data from one data source to another, into a database. So in our example, we're moving data from the blockchain into a Postgres instance. That's the way the graph works. So You don't need to know the details, just know that. We need to somehow take this data from the blockchain, put it into this instance so that then we can query for it. So the ETL pipeline is 3 steps: extract, transform, load. Just keep that in mind. And this is what we do with the graph. So the first problem that has to be addressed when we're talking about subgraphs and kind of the graph, and I would say the number one issue I've heard with people trying to use subgraphs is that if you have a really large data set, your subgraph could take a long time to sync. It could take a long time to actually like index all of these events, and it could take days or weeks even. So for some teams it wasn't a great fit because they have a lot of data, they needed like almost instant like results, and it just wasn't working for them. And the problem is for this specific case is that all of these steps in the ETL pipeline, the way it stands with the graph and with subgraphs, is they're all done in a single unit of computation in these mappings, in these transformers, in these resolvers that we talked about. You can call them transformers. So because of this, because it all happens in one unit of computation, this has to be done linearly. So when you're talking about 15 million blocks times 7 at least, times 70 at least transactions, like that's a lot to go through linearly. And computer science people in here, O of n is never good, especially when we're talking about something this big that's going to continue to grow. The second problem is that the ETL pipeline works at an isolated level, and as of now, there was no way to connect the data at the indexing layer rather than the consumer level. So what that means is you could have, maybe your dApp deployed on multiple different networks, and you're going to have to write a separate subgraph for each one because you have one on maybe Polygon, maybe on mainnet, and I don't know, maybe one on some testnet. And the issue is that you would have to rewrite all of these and kind of merge these together in your UI, right? Your user wouldn't know that there's 3 different subgraphs because you just display it however you want. But at the developer level, there's no way to connect these at a lower level. You can only connect them at the, at your client application level. The third problem is that subgraph developers would often have to rewrite code because you can imagine for anything like this open API that we're talking about, there's some steps that you always have to do. You probably always want to get someone's wallet address. You probably always want to know someone's token count. Like things that are kind of common, you would have to rewrite them a lot. And we would see that subgraph developers would often just fork other subgraphs and then try to work off there. So we noticed, okay, this is problematic. And kind of the solution that we are unveiling, or not unveiling, it came out at Graph Day maybe like a month ago, but that I'm here to talk to you guys about is our Substreams. So Substreams were created by another core developer called Streaming Fast, and they worked on the Firehose technology, if you guys are familiar with that, and they're super amazing, super smart team, and I'm going to try to do their technology justice here. Like I said, I'm from Edge and Node, so I usually have a different focused talk, but this was really cool and important, so I wanted to kind of try to do them justice. So Substreams are fully parallelizable, infinitely composable, and highly reusable data units. These substreams are written in Rust. Everyone loves Rust. Rust is super fast, but really the key here is that they're parallelizable. So instead of having to do this indexing linearly, we're now cutting the time by a bunch because instead of having to wait for one block to finish processing to move on to the next, we can do these all in parallel. The other cool thing is that these are composable and reusable, and we'll talk about this in a bit. So going back to the problems that we kind of just talked about, the first one was about this, O of n, processing time, and it takes too long. So with Substreams, these individual modules allow a community to build higher order modules, and like we said, we'll talk about this more in a second. You'll understand what I mean when I say these modules can be parallelized because we're breaking down this entire subgraph from this kind of like linear processing to different modules that create this tree. The second solution is that these composable modules make it possible to connect the data at the indexing layer. So now you don't have to wait until your subgraphs are deployed to then try to put them together in your UI, but still have to write 3 different ones. And then finally, these modules are written and can be shared, allowing other developers to use the modules that you or other developers have made. So they kind of have this vision for like npm install, and then you can just use someone else's things. So things that are common that you are probably going to have to rewrite often, or if you're building for a very specific use case, you might have to build this thing often. You can just build it once and then reuse it multiple times. And defining modules real quick. I say the word modules, but what does that mean? Modules are small pieces of code running in a WebAssembly VM amidst a stream of blocks arriving from the blockchain node. So when we think of the word like streaming fast, that's their org, substreams, it's this constant stream of data, in which I'm not going to get into the specifics here, but at the end I link really good documentation if you want to kind of learn more about how that works. And then there's two module types. And these modules, like we said, are composable, and you can kind of play with them like Legos to do the things that you want. So the first type is a map. It maps elements from one representation, initially a block. You get the entire block, which we'll talk about in a second, to a different implementation. And then the second type is a store. It stores information and specifies the merge strategy for how stored elements should be merged together. Modules have a single output that can be typed, and they inform consumers, aka the module that's going to consume the output of this, what they should expect. So you can think of this as like a stream of water or something that's like flowing downwards. It has one input and then it outputs something. It can have multiple outputs, but then the other modules that are receiving these outputs, they're meant to receive outputs from other modules. So that in that sense, they are composable, and in that way you can kind of like mix and match. You can use different modules. You can kind of build it step by step in a way that you can abstract out certain things depending on your use case, rather than kind of the monolithic linear model that we had just talked about. And then modules can also take multiple inputs like this one. But really what's cool is that with substreams, you can unlock generic substreams. So before, like I said, with the graph, you had to pass in a contract address. So if you just wanted to do kind of like a generic subgraph, like, oh, I don't know, give me all, I don't know, the average gas price for certain blocks, and kind of just want to know all the different NFTs that were traded, you would have to take the contract of all the NFTs that you wanted to be included. There's no way to be like, just give me all the NFTs, give me all of the transfer events here. You needed to define this data source. So with substreams, you kind of unlock this ability to be more generic. So you receive the full block with substreams, and then you as a developer, you filter out what you need or what you don't need from the block. And then finally, the output or extraction of one module becomes the input of another module, creating this effective pipeline of data flow. Okay, and then when we're talking about index performance improvement, you don't even have to read the slide. The point is, parallelized, way faster, that's just it. Not linear, composable, you can put these together, and then these modules execute independent of each other. And then when the output, so, right, this creates a dependency tree. This creates a tree of modules. Obviously, some modules are waiting for the output of other modules, but generally, this is way more parallelized than what we had before. And then, like we said, the whole subgraph is split into these smaller modules, and the whole of these modules creates this dependency module tree. So to recap, you write these in Rust. They're brand new, just dropped like a month ago or something. We're still, me myself, I'm still playing with these and doing a lot of stuff. So if you're interested in these, I would follow myself on YouTube, because that's where I post a lot of what I'm learning and what I'm working on. So I'm definitely going to be doing stuff right there. And finally, I'll leave this slide up. So I know you guys can't click these, but I'll tweet this whole presentation so that you can then click on these links. But here I have the documentation for substreams, and then I also have building a subgraph workshop. So I think it's kind of like important just to go through the process of building a subgraph, so then you can see how it's different from using substreams. It's kind of hard to, I would think, to conceptualize using substreams for the first time if you don't really know the problem that it's solving, or if you haven't really run into that. So here I also have a workshop where it walks you step by step for how to develop a subgraph. And yeah, thank you.
Any questions?
Okay, I'm going to preface this. Don't be asking me no hard questions, okay? These just came out. Okay,
how are you today? No, I wanted to ask a question about the data architecture. So the starting point was this Etl pipeline that extracts, transforms, loads the data into Postgres. So my question is, would the graph also allow for an ELT pipeline, where you first load the raw data into the database and then you model the data afterwards? Because I imagine that like a lot of different projects they want to access the same loaded data, but they have different transformations on this data. So then I guess the compute kind of like blows up because of that.
That's a good question. I don't have the answer for you, but I'll find out. But kind of from my understanding, I think that, okay, so you still write a schema, as part of this process. So I kind of want to say, I don't know. I don't want to say the wrong thing. I'll find out for you. I don't know.
Thank
But
you.
I'll find out, yeah. Any other questions? Great. Oh, my God. I just tell people, I'm like, don't ask me questions while I'm up here. I'm still figuring it out. But yeah, so this is by Streaming Fast. They are a really cool team. You can tweet them. They are like super helpful. They've been helping me kind of get started and like use them and play with them. You can also come to me for questions and I'll go to them, the back end, answer them. All right, thanks y'all.
Thank you.